Welcome students to the fourth lecture on determinants. In the last lecture, we have solved several problems on computing determinants of 3 cross 3 matrices, but the techniques developed there can be extended to solve for n cross n square matrices also. In today's lecture, we shall look into determinants from different angles. Let us look at first from areas of triangles. We know the area of a triangle given by points x1, y1, x2, y2 and x3, y3 is half into x1 into y2 minus y3 plus x2 into y3 minus y1 plus x3 into y1 minus y2. This we have seen in our coordinate geometry. Question is how we can see it from a determinant perspective. Consider the following matrix. One, 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 x1, y1, x2, y2 and x3, y3. So, what we have done? We have taken the 3 points, but of course, we have taken an extra column 1, 1, 1 as the first column. So, what is the determinant of this matrix? If we call it A, then determinant of A is equal to 1 into x2 y3 minus x3 y2 minus 1 into x1 y3 minus x3 y1 plus 1 into x1 y2 minus x2 y1. This is equal to x2 y3 minus x3 y2 minus x1 y3 plus x3 y1 plus x1 y2 minus x2 y1 is equal to, if I now take x1 common from these two terms, I get x1 into y2 minus y3 plus I take x2 to be common from these two terms plus if I take x3 common from the two remaining terms, we get this. Therefore, if we compare with the formula for area of a triangle, we get that area is equal to half of the determinant of 1 x 1 y 1 1 x 2 y 2 1 x 3 y 3, or it is same as half of x 1 y 1 1 x 2 y 2 1 x 3 y 3 1. In some books you may get it like that. I have done it like this, but if we look at carefully, we will see that these two values are actually same, because here if we swap the first column with the second column, we know that 1 1 1 will come here, x 1 x 2 x 3 will come here. Then after that, if we swap the second and third column, I will get y 1 y 2 y 3 here and 1 1 1 here, and we know that if we interchange the two rows or interchange two columns, then the determinant gets a negative side. Since we have to do it twice, eventually we will get the determinant with the same sign. If determinant comes out to be negative, we take the absolute value for area. That is obvious, because area of a matrix cannot be negative. What happens if the determinant is 0? Area of a triangle will be 0 if the points are collinear. Therefore, to test collinearity, we may use determinant in the above way. Example, show that A is equal to A comma B plus C, B is equal to B comma C plus A, and C is equal to C comma A plus B are collinear. Therefore, we will compute the determinant of one A B plus C, 1 B C plus A, 1 C A plus B. Now, by doing C 3 is equal to C 3 plus C 2, this determinant is equal to 1 A plus B plus C, 1 B A plus B plus C, 1 C A plus B plus C is equal to A plus B plus C into determinant of 1 1 1 A B C 1 1 1, which is 0 as these two columns are same. Therefore, we can see that these 3 points are collinear as the triangle formed by these 3 points has area is equal to 0. Another example, if points A comma 0, 0 comma B and 1 comma 1 are collinear, then show that A plus B is equal to AB. Since these are collinear, we know determinant of 1 1 1 A 0 0 B 1 1 is equal to 0. By replacing R1 by R1 minus R2, we get the determinant is 0 A minus B 1 0 B 1 1 1. Now, by replacing R3 with R3 minus R2, we have the determinant is same as 0 A minus B 1 0 B 0 1 1 minus B. Now, by expanding with the second row first column element, we get determinant is equal to minus 1 to the power 1 plus 2 into 1 into A into 1 minus B minus 1 into minus B is equal to minus 1 into A minus AB plus B. So, equating with 0, we have A minus AB plus B is equal to 0 or A plus B is equal to AB. This is what we have been asked to show. Another example, use determinant method to find equation of the line joining points A is equal to minus 2 comma 4, B is equal to 2 comma minus 6. We know from our knowledge of coordinate geometry the equation of the line is y minus 4 upon 4 plus 6 is equal to x plus 2 upon minus 2 or y minus 4 upon 10 is equal to x plus 2 upon minus 4 or 10x plus 20 is equal to minus 4y plus 16 or 10x plus 4y plus 4 is equal to 0. This in any case we know, but now we do it using determinant and see whether we get the same result. So, let x comma y be any point on the line joining minus 2 comma 4 and 2 comma minus 6. Therefore, determinant of 1 minus 2 4, 1 2 minus 6 1 x y is equal to 0 or 0 minus 4 10 1 2 minus 6 1 x y. This determinant is equal to 0 by making R1 replaced by R1 minus R2 or determinant of 0 minus 4 10 0 2 minus x minus 6 minus y 1 x y is equal to 0. This is by replacing R2 with R2 minus R3. Now, what is the determinant of this matrix? This is actually the determinant of these 2 by 2 submatrix, or minus 4 into minus 6 minus y minus 10 into 2 minus x is equal to 0, or 24 plus 4y minus 20 plus 10x is equal to 0, or 10x plus 4y plus 4 is equal to 0. Therefore, this is the equation of the line passing through the two given points minus 2 comma 4 and 2 comma minus 6, and this is the same result that we have got after applying our knowledge of coordinate geometry. So, this way also we can compute the equation of a line passing through two given points. Let us take another example. If the area of the triangle A minus 2 comma 4, B 2 comma minus 6 and C 5 comma k is 35 units, or 35 square units, what is the value of k? Therefore, we know that we can get the area by using determinant, that is, what is given is that half into 1 1 1 minus 2 4 2 minus 6 5 k is equal to 35, or determinant of 1 minus 2 4 1 2 minus 6 1 5 k is equal to 70, or determinant of 0 minus 4 10 1 2 minus 6 and 1 5 k is equal to 70, as before I have done rho 1 is equal to rho 1 minus rho 2, or determinant of 0 minus 4 10 1 2 minus 6 0 3 k plus 6 is equal to 70. This we get by doing R3 is equal to R3 minus R2. Now, we try to find the determinant. Since we have only A21 is non-zero, its determinant is going to be minus 1 times this into this and this into this, or minus 1 into minus 4 times k plus 6 minus 3 into 10 is equal to 70, or minus 1 into minus 4k minus 24 minus 30 is equal to 70, or 4k plus 24 plus 30 is equal to 70, or 4k is equal to 16, or k is equal to 4. That is the answer. Okay, students, let me now introduce you to the terms minors and cofactors. If you remember, we have expressed the determinant of a matrix A as sigma over j is equal to 1 to n A1 j into minus 1 to the power 1 plus j into m1 j, where m1 j is the determinant of the submatrix of A after deleting row 1 and column j. In a similar way, we can also write determinant of A is equal to sigma over j A I j minus 1 to the power I plus j into m I j by expanding along row I. Similarly, we can do it by expanding along a column also, but what is important is that the term A I j is being multiplied by minus 1 to the power I plus j into determinant of the matrix which we obtain by deleting the ith row and jth column. This m I j is called the minor corresponding to the element A I j. Therefore, definition: for a given matrix A, if we consider the element A I j, that is at the position ith row and jth column, then corresponding minor m I j is the determinant of the n minus 1 cross n minus 1 matrix obtained after deleting ith row and jth column of A. Also, we have seen that in the expansion of the expression for determinant of A, we multiply A I j with minus 1 to the power I plus j into m I j. This whole thing is called the cofactor corresponding to A I j. Example, consider the matrix A is equal to A, B, C, D. Therefore, determinant of A is equal to A D minus B C. Therefore, M 1 1 is the minor for this A, is the determinant of the submatrix after deleting the first row and first column, is equal to D. M 1 2 is equal to the determinant of the submatrix after deleting first row and second column, is equal to C. M 2 1 is equal to the determinant of the submatrix after deleting column 1 and row 2, is equal to B, and M 2 2 in a similar way we can get is equal to A. But what are the cofactors? The cofactors are A 1 1 is equal to minus 1 to the power 1 plus 1 into M 1 1 is equal to D. A 1 2 is equal to minus 1 to the power 1 plus 2 into M 1 2 is equal to minus C. A 2 1 in a similar way we will get is minus B, and A 2 2 is equal to A. So, that is the subtle difference between the minors and the cofactors. Let me ask you a simple question. If A is equal to A 1 1, A 1 2, A 1 3, A 2 1, A 2 2, A 2 3, A 3 1, A 3 2, A 3 3, which of the following gives determinant of A? Option A, A 2 1 into M 2 1 plus A 2 2 into M 2 plus A 2 3 into M 2 3. That is, I am trying to expand it along the second row, but we find that the signs have not been taken care of. Here we should have been minus 1 to the power 2 plus 1, therefore, there should have been a minus here, there should have been a minus here, therefore, this is not correct. Option B, A11 into M11 minus A12 into M21 plus A13 into M31. As we can see, it has taken care of the sign. Here it is going to be positive because 1 plus 1, here it is going to be positive because 1 plus 3, these are even. So, minus 1 to the power an even number makes it 1, but here it is 1 and 2, therefore, the minus sign is there. But here the problem is A12 is multiplied by the cofactor M21, which should have been M12. Therefore, this is also wrong. Option C, A31 into A31 minus A32 into A32 plus A33 into A33. Here instead of minors, we are using cofactors. Therefore, the minus sign is already taken care of inside the cofactor. Therefore, this minus is wrong. Therefore, this also does not give us the correct value of the determinant. Option D is A13 into A13 plus A23 into A23 plus A33 into A33. If we look at that, we can understand that we are expanding along the column number 3 and each term has been suitably multiplied by corresponding cofactors. Therefore, this is the right answer. Therefore, answer is option D. Let me now introduce a new concept which is called adjoint of a matrix. Definition: the adjoint of a square matrix A is defined as the transpose of the matrix Aij, where Aij is the cofactor of Aij. That is, if A is equal to A11, A12, A13, A21, A22, A23, A 3 1, A 3 2, A 3 3, then adjoint of A is the 3 cross 3 matrix which is A11, A12, A13, because we are writing as the transpose A21, A22, A23, A31, A32, A33. Example, if A is equal to A, B, C, D, then A11 is equal to D, A12 is equal to minus C, A21 is equal to minus B, and A22 is equal to A. Therefore, adjoint of A is the matrix D minus C minus B A, that is, the diagonal elements are interchanged and sign of diagonal elements are changed. Thus, for a 2 cross 2 matrix, we get the adjoint very easily. Now, what is the product of A times adjoint of A? So, let us do it. We have A is equal to A, B, C, D, and adjoint of A is equal to D minus C minus B A, and if we multiply this, we get a 2 cross 2 matrix which is AD minus BC minus AB plus AB plus CD minus CD and minus CB plus AD is equal to determinant of A 0 0 determinant of A. That is, it is a diagonal matrix with diagonal entries equal to determinant of A. Therefore, For our 2 cross 2 matrix, we see that A into adjoint of A is equal to determinant of A into I, which is the identity matrix of size 2 cross 2. In general, if A is n cross n, then also we find A into adjoint of A is equal to determinant of A into an identity matrix of size n cross n. Let me verify the result. For 3 cross 3 matrix. Therefore, let P be the product of A into adjoint of A, that is P is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33 into A11, A12, A13, A21, A22, A23, A31, A32, A33. What is the value of P? As I said, it is going to be the determinant of A into I3. We want to verify that P is equal to determinant of A into 1 1 1 0 0 0 0 0 0. Let us look at the P11. If we look at this, it is A11 into A11, A12 into A12 and A13 into A13. P11 is equal to A11 into A11 plus A12 into A12 plus A13 into A13, which we know that is the expression of the determinant when we expand along the first row of A. Therefore, this is going to be determinant of A. Similarly, P22 and P33 can be shown to be determinant of A. We need to show that off diagonal elements are 0. I verify with P12. So, what is P12? P12 is equal to A11 into A21 plus A12 into A22 plus A13 into A23 is equal to A11 into minus 1 to the power 2 plus 1 determinant of A12, A13, A32, A33, because this we get from the adjoint of A21 plus A12 into minus 1 to the power 2 plus 2, because we are computing the adjoint corresponding to A22, and therefore, determinant of A11, A13, A31 and A33 plus A13 into minus 1 to the power 2 plus 3, because we are doing it for A23, and therefore, it is going to be A11, A12, A31, A32. Now, let us expand it. This is coming out to be minus A11, A12, A33 plus A11, A13, A32 plus A12, A11, A33 minus A12, A13, A31 minus A13, A11, A32 plus A13, A31, A12. Now, let us look at the terms. We find that minus A11, A12, A1, A33, and this is plus A12, A11, A33. Therefore, they cancel each other. This is A11, A13, A32, and this is minus A13, A11, A32. Therefore, they also cancel each other. This is minus A12, A13, A31 is equal to plus A12, A13, A31. Therefore, this also cancels with this. Therefore, this whole thing is equal to 0. So, this I have verified for P12. I suggest that you convince yourself by working out on other off diagonal elements and computing their values, which you will see that will come out to be 0. Therefore, A into adjoint of A is equal to determinant of A into I3. Okay, students, I stop here today. In the next class, I will talk about inverse of a matrix, and then I will show certain properties of it and how we can use it in solving system of linear equations. Okay, students, thank you.